Good morning to all. Today we'll be discussing about the fourth part of thin cylinders, which is a part of theory of structures subject. So before going into the lecture, once we'll revise the last class, what all we have learnt in the last class. So in the last class, we have learnt how to calculate circumferential strain, longitudinal strain, change in length and change in diameter. There is nothing but change in dimensions of the cylinder using various formulae. So we have solved some numericals based on types of stresses and types of strains. So in this class, as I have mentioned in the previous tutorial, I'll be explaining about or I'll derive the equation for volumetric strain. So what is meant by volumetric strain initially? When the thin cylinder is subjected to the internal pressure, as we have already calculated that there is a change in cylinder dimensions. So that is due to longitudinal strain and hoop strains come in come into picture. So as D becomes D plus delta D and L becomes L plus delta L, we'll get change in volume, and because of that we'll get a volumetric strain. So as a result of which there will be change in capacity of the cylinder. There will be change in capacity, which is nothing but volume, or there is a change in the volume of the cylinder. Hence it becomes imperative to determine the change in volume or the volumetric strain. So because of hoop stress and longitudinal stress, there are certain strains that are nothing but change in dimensions. Because of such stresses and such strains, there will be a change in dimensions which results in change in the capacity or volume of the cylinder which we are using. So as it is a continuous process, you need to measure the changes in the dimensions and also the volume to know the exact capacity of the cylinder or the limits of the cylinder. That is nothing but how much strains it is undergoing. Such things we need to take care. So if we go into the description of the volumetric strain, the capacity of a cylinder is defined as capacity is nothing but volume. As you all know, volume is equals to area into length. So here our cross section is cylinder circular and we have the area as pi d square by 4 into length. So this is our original volume. This is a original volume or initial volume. So from this, what will be the changes after undergoing certain strains? Let there be a change in dimensions occurs when the thin cylinder is subjected to an internal pressure. So the diameter D changes to the D plus delta T, and the length L changes to L plus delta L. So because of these changes, there will be a change in volume. Therefore, the change in volume equals to final volume minus initial volume or original volume. So this change we need to calculate ultimately. So you can see the equation here, final volume minus original volume. If we write or if we substitute the exact value, this is what we get. So final volume, as D has become D plus delta D and L has become L plus delta L. If we substitute those values here, the value will be pi by 4 D plus delta D square into L plus delta L minus original volume, that is pi by 4 D square L. But we already know strain is change in dimension by original dimension, and here we are discussing about volumetric strain. So volumetric strain will be change in volume by original volume. So this will be our change in volume equation, and original volume equation already we have. If we substitute those things into this equation, we will get this particular relation. So after substitution and taking certain common terms outside, like pi by 4 gets cancelled and the rest of the things are written here. So d plus delta d whole square into L plus delta L minus d square L into L by d square into L. So after multiplication, we'll get this particular equation. I mean, if we elaborate this equation, we'll get this equation. So here we can neglect some negligible values like delta D and delta L are already they are very small quantities, and the squares of such small quantities will become much more smaller. So simplifying and neglecting the products and squares of small quantities, that is delta L and delta D. So here we have neglected this particular term, and some terms will get cancelled. So ultimately we'll get an equation of 2D into delta D into L plus delta L into d square by d square L. So if you separate these terms, ultimately you'll get as delta L by L plus 2 into delta d by d. So if you keenly observe this term or this equation, hoop strain, which we have discussed earlier, is equals to what? Delta d by d. In the same manner, longitudinal strain epsilon L equals to delta L by L. So by definition, delta L by L is equals to longitudinal strain and delta D by D is hoop strain. So these two terms you can see in this equation. So with respect to this, we can write volumetric strain is equals to longitudinal strain plus 2 times of hoop strain, right? So we also have certain hoop strain and longitudinal strain values or equations as PD by, like this. If I show you, I mean these equations. Okay, so longitudinal strain is PD by 2TE into 1 minus 1 by 2M, and longitudinal strain is PD by 2TE into 1 by 2 minus 1 by M. So that is PD by 2TE into 1 minus 2 mu and PD by 2TE into 2 minus mu. Hello, చెప్పండమ్మా. చెప్పండి చెప్పండి. ఎస్ 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 కంప్లీట్ చేశాను. నిన్న మీరు ఆల్రెడీ ఫోన్ చేశాను నాకు. So if we substitute these values in this equation, I guess here there are some mistakes in this, which is wrong. This should be 2t. Okay, whatever. Yeah, if we substitute these two values in this equation, we'll get as PD by 4TE into okay, whatever, 1 minus 2 nu plus there's some mistake in this, so then don't get confused here. Already you know epsilon h and epsilon L values, you simply substitute those values here. Okay, PD by 40E into 1 minus 2 mu, and here mu is written as nu. Poisson's ratio, it can be written as 1 by m also, so no need to get confused. Both are, all the three are 1 and 7 into 1 minus 2 nu plus 4 minus 2 nu, which gives us PD by 40E into 5 minus 4 mu. So this is the ultimate equation for volumetric strain. And what is volumetric strain again? If you write like this, change in volume by original volume, or this should be delta V, right? Change in volume by original volume. So change in volume is equals to PD by 40 into 5 minus 4 mu into volume. So this is what we need to calculate. This gives us the change in volume of the cylinder after undergoing various strains. So therefore, to find the increase in capacity or volume, multiply the volumetric strain by original volume. That is what I have mentioned in this equation. So to find out the increase in capacity or volume, multiply the volumetric strain, nothing but sigma V into V, will get change in volume, right? So hence change in capacity by volume or volume can be written as increase in volume is equals to PD by 40E into 5 minus 4 mu into V, nothing but volume. This is original volume, remember that. Or change in volume can also be found out if you have directly hoop strain and longitudinal strain values. You can also solve the change in volume by using this equation, because we have a relation of volumetric strain as this here, right? So we can use this equation as well. So change in volume is equals to original volume into longitudinal strain plus 2 times hoop strain. So this is the another important formula of this chapter, which you have to remember, and also the derivation is very important. So that's why I have explained this in a separate tutorial. So ultimately we have found out the change in volume of the cylinder, which is subjected to an internal pressure P, and also which is undergoing certain changes in dimensions due to various stresses. So based upon this knowledge, we shall try to solve some numericals. A thin cylindrical shell of diameter 150 mm and length is 1.2 meter and thickness is 6 mm. Is full of oil at atmospheric pressure. Is full of oil. Find additional volume of oil that should be pumped into the cylinder so as to increase the pressure to 7.8 Newton per mm square. So P is this much, and rest are all values he has given: E value, Poisson's ratio, and bulk modulus of oil value he has mentioned. So here you need to observe the question keenly. What is asking? Is asking find the additional volume of the oil so that it should be pumped into the cylinders to increase the pressure to certain value. So if we go into the solution, given diameter is 150 mm, length is 1.2 meter, that is nothing but 1200 mm, thickness is 6 mm, and P is 7.8 mm, and E, mu and K values are given. So initially if we find out the original volume of the oil before pumping, nothing but as the oil is, why we are calculating this volume of oil here, because he has mentioned the can is full of oil, which is nothing but volume of oil equals to volume of cylinder, right? So this condition helps us to write this equation. So volume of oil at nothing but volume of cylinder at atmospheric pressure V is equals to pi d square by 4 into L. So if you substitute d value and L value, we will get certain volume. So for cylinder, he has asked us to calculate the additional volume of oil to be pumped. As the cylinder is already full, how we can pump some more additional oil into it? Only if there is a change in the dimensions of the cylinder. So only if there is a change in volume of the cylinder, we can pump additional oil into the cylinder. So for that we need to calculate the change in volume of the cylinder, which is nothing but, for that we need to calculate volumetric strain. So for cylinder, volumetric strain is equals to delta V by V. So for cylinder, you can mention it as delta V1, which is nothing but equals to epsilon V1. So that is PD by 2TE, or D by 2 can be written as R, radius, one and the same, is equal to 2TE into 5 by 2 minus 2 mu. No need to get confused. This equation and the equation which we have derived here, both are same. Just a small manipulation in this, right? So if you substitute all the values, P D by 2 R, nothing but 15 by 2 7, this is 2.5, and M at 2 M 1 by M is 0.3, and ultimately substitute 6 and E value, we will get certain volumetric strain. So this is our epsilon V1. So to calculate the change in volume of the cylinder, that is delta V1, we need to multiply this strain into original volume. Original volume we have here. So 0.00195 into original volume gives us certain value. So this is the change in volume of the cylinder because of strains. So for oil, we can calculate how much oil, extra additional oil we need to calculate now. So for that we can calculate, we can use this bulk modulus relation. As you already know, bulk modulus is equals to pressure by volumetric strain. So this relation will be useful for us to calculate the change in volume of the oil, or I mean to say additional volume which we need to add. So that is why he has given the bulk modulus value. So K is equals to pressure by change in volume by original volume. So by using this equation, ultimately we need to find out this delta V2. So for delta V2 equals to P by K into V, right? So this we have mentioned here. This is the equation. So delta V2 by V equals to P by K. P is 7.8 and K is 2.6, and delta V2 is equals to V, already we have this value, into this, we'll get certain volume of the oil. So therefore volume of the oil to be pumped will be volume of oil except chain extra oil plus gain volume of the change in volume of the cylinder. So if we add these two only, 1 and 2, again the cylinder will get filled with the oil, right? So that is why we need to add 1 and 2. So delta V is equals to delta V plus delta V2. So if we add these two values, we are getting 104968.45 mm cube. So this much additional oil need to be filled in the cylinder to achieve a pressure of 7.8 Newton per mm square. I hope this thing is clear, or else once you solve this problem by your own, so that concept will be clear for you. The only thing which you need to observe here is why we are calculating the two volumes. I mean change in volume of the cylinder and change in volume of the oil, because as the cylinder is subjected to, initially cylinder is filled with oil completely, right? So now what he is saying, yes, put an condition that a pressure should be of 7.8 inside the cylinder. P should be 7.8. So as it is subjected to certain internal pressure, there will be a change in volume of the cylinder, right? So if there is a change in the volume of, as we already know, that change will be in positive side itself. That means it will elongate or it will enlarge. So again, after enlarging, there will be a gap of oil in the cylinder, right? So after enlarging, there is a gap here. Now we need to calculate this additional volume of the oil to be pumped into the cylinder so that we can achieve this internal pressure. So that is why we are calculating two volumes, which is one is delta Vc, the change in volume, and again this volume delta Vo, nothing but oil, change in volume of the oil which we need to add into the cylinder. So by adding these two values, we'll get ultimately how much oil we need to pump into the cylinder. So with this knowledge, we'll again solve one more numerical. A thin cylindrical shell of thickness 6 mm and diameter 400 mm is subjected to an internal pressure which produces a strain, okay, in diameter. In diameter means strain in terms of diameter means he has given epsilon h, that is delta d by d equals to 1 by 2 times 2500. So instead of giving internal pressure value directly, he has mentioned the strain in the diameter. I mean to say strain in terms of diameter. So find the internal pressure and consequent hoop and longitudinal stresses. So he has given hoop strain. He is asking us to solve hoop stress and longitudinal stress. So take E is equal to 2 into 10 power 5 Newton per mm square and mu is equals to 0.3. Right. So T, D, and we need to find out P, FH and FL. Strain in diameter is equals to strain in the circumference. I already mentioned here, right? So strain in diameter is equals to strain in circumference. Nothing but epsilon h, which is equals to PD by 2TE into 1 minus 1 by 2 m, right? And this value he has given already, which is 1 by 2500, which is equals to PD by 2T into 1 minus 1 by 2 m. P we need to find out. D already we have 400 by 2 into T, which is 6, into E, which is 2 into 10 power 5 into 1 minus 1 by 2 into mu, that is 0.3. So after substituting all these values, we can find out P, and ultimately we'll get a value of 2.8235. Newton per mm square. So this is our internal pressure in the cylinder. And next we need to calculate hoop stress and longitudinal stress. As we already have p value, rest is very easy, simply substitution. As hoop stress is equals to pd by 2t, p we have, d we have, and t also we have. So we are getting a value of 92.12 Newton per mm square. The units are very important here. So again, longitudinal stress FL is equals to PD by 40 P T and by 4 times of T. You'll get a value of 47.06 Newton per mm square. So we have solved each and everything here, right? So this is one solution, this is another, and this is the third one. We'll solve one more numerical, which is very small one, but a bit tricky one. A 100 mm diameter copper pipe is 10 mm thick. It is subjected to an internal pressure and as well as external pressure respectively. So find the maximum stress in the metal. Without looking into the answer solution, just try to remember the relation between hoop stress and longitudinal stress. Hoop stress is equals to 2 times of longitudinal stress. So here the maximum stress will be hoop stress. So instead of mentioning here hoop stress, he is asking us to find out maximum stress in the metal. So we need to calculate hoop stress. And also he has mentioned that the cylinder or the copper pipe is subjected to two pressures. One is internal and another is external. So the net we need to calculate. So net or resultant pressure will be internal minus external. So 2 minus 0.9 will get 1.1 Newton per mm square. So D he has given already 100 mm and T 10 mm. So maximum stress I have mentioned earlier, which is hoop stress sigma h or Fh is equals to PD by 2T. So P is 1.1 and D is 100, T is 10. We get a value of 5.5 Newton per mm square, right? So you may get a doubt that what if external pressure is greater than internal pressure? I mean to say, if these two values get interchanged, we'll get a net result as minus, right? So in such case, pressure generally it won't be in minus conditions. So in such case, there won't be any stresses developed in the cylinder. So no need of calculating all these things, right? So This is a small question, but bit concept involved in it. So I thought of sharing it with you. So you should not get confused. Find if we ask find the maximum stress in the metal. So you should not confused with the maximum shear stress or something else, right? Yeah, it simply mentioned calculate the maximum stress itself. We didn't mention any maximum shear stress or like that. So here you need to use your concepts, the basic concepts which we have studied in previous tutorials. So maximum stress will means either hoop stress or longitudinal stress. So in that you need to find which one is maximum and simply you need to use that equation to calculate. So before concluding this tutorial, once we'll see the summary, I mean what all we have studied in this tutorial. So in this class we have learned circumferential strain or hoop strain, the equations we have seen, and also some numericals based on such strain values. We have used these relations to solve certain numericals, and most importantly we have derived this equation, right? We have derived this particular equation, which is very useful for your examination point of view. So we have derived an equation for volumetric strain actually. Which is equals to delta V by V. So delta V is change in volume or capacity, which is nothing but delta V is equals to original volume into hoop strain, I mean to say longitudinal strain, plus 2 times of hoop strain, right? Or there is another equation for this, PD by 4 times T into 5 minus 4 mu into original volume P. So depending upon the values which they are mentioned in the question, we can use either this formula or this formula. So I hope these topics are clear now, and try to solve some more numericals by your own after once revising this tutorial and the numericals. I hope you'll be solving any other numerical based on such topics, and once try to revise your basics, that is what is meant by bulk modulus, what is meant by Young's modulus, and what are the relations, right? So because bulk modulus equation we have used in one of the numerical, you need to know such relation, unless you won't be able to solve such problems. So basics are important here, and also the units, particularly each quantity and their units you need to be perfect with. So with this I will conclude this tutorial here, and I'll see you in the next class with some other topic. I hope most of the thin cylinders topic is covered till now. If there are any leftovers according to the syllabus, I'll try to complete that in the next tutorial. So by that time, you'll be able to complete everything in this particular topic. Thank you all.